Greetings. My name is Akshay, and I'll be explaining on the topic the translation Lookaside Buffer, also known as the TLB. So I thought this is an interesting topic because of how the process is structured, how the steps are given very clearly, and how the whole concept of TLB fits um, eh, perfectly in the paging process, and it gives us a beautiful solution to a complicated problem. So let's look into the TLB. So in operating systems, the memory management, to be specific in paging. So in the process of paging, there are some things called page tables. So page tables are created for each process. So basically, paging is when we use the main memory, when we use the secondary memory to store some of the data, and we have mapped the data stored in the secondary memory in the main memory. So for ease of access, we need it to be mapped so that we can know exactly where to look and retrieve it from there. That is why we have page tables. So there is a page table for each process, and using this page table we will be able to retrieve the processes. So this page table will contain information like the frame number. So this will be the address of the main memory where we want to refer, and there will be some other useful bits also there. These useful bits may be like the parity bit, the valid invalid bit, the protection bit, or so on. So the page table also has something called the page table entries. That are the information present in the page table, which tell us where in the main memory the page is actually residing. So now the question is where to place the page table. See, so after all, page table is also a data structure, and it also requires some storage. So the page table also needs to be stored in some place. Only then it can be taken and referred to, and only then we can see where the data is being stored. So the page table also needs to be stored in some place. Even though page table is so useful for the mapping purpose, it also needs some storage space. So where do we store the page table? One must keep in mind that the page table itself is invented to make the retrieval process quicker. So we cannot place the page table in a less efficient storage space like the secondary storage, or somewhere where it is inefficient or takes a lot of time to retrieve. So it needs to be placed in a very efficient storage space. So that is where we get the question now, where to place the page table such that the overall access time or reference time is reduced, is very less. So that is where we come up with the problem, where to place the page table. The problem initially was for the fast access of the main memory content based on the address generated by the CPU. That is the logical address that it is generated. Initially, there were some ideas given by people. Uh, they had the thought of using registers for storing the page table, because, as we know, registers are very efficient and high speed in their retrieval process. So, as we know, the fastest is the CPU, and then we have the registers, then the cache, and so that is how the data storage pyramid is. So registers are right next to the CPU, and they are the fastest, almost one of the fastest storage devices. So initially there was a thought of storing the page tables in the registers itself. However, there are problems in storing it in registers also. The problem being the registers are not big enough. The idea of using registers was not practical, because the everything seems to be right, but the problem is register size is very small. So in practical it can accommodate only 0.5k to 1k page table. So that may not be enough, because some processes may be very huge, that they may have so many page entries, like page table entries, that it might not be enough to just use the one register for a page table. So that is where it runs into an issue, and it is not practical anymore. Like, it was okay in theory, but when we start using it may not be practical. So that is where we needed a solution. And this was the problem, and the solution to that was the topic of the day for us, the TLB, that is the translation Lookaside Buffer. So yeah, the TLB, the translation Lookaside Buffer, is nothing but a special cache. So the TLB is also a type of cache. So it is very similar to the normal cache, but its purpose is specific. Like the normal cache is used for everything, but here it's specifically used for the page tables. It is used to keep track of recently used transactions. The TLB contains page table entries that have been most recently used. So it almost runs like on the algorithm of the most recently used. So the if it has not been used for a long time, then it is removed from the TLB. Okay, so given a virtual address, the processor examines the TLB if a page table entry is present. That is, if there is a TLB hit. If there is a hit, then the frame is retrieved and the real address formed. If in case it is not present in the TLB, then it becomes a TLB miss, in which case it will update the TLB with the data, but it has to fetch the data from the secondary memory, which is inefficient. But mostly it is a TLB hit. So all those cases we have saved a lot of time and retrieval resources. But when there is a miss, again we have to go to the secondary. It has to go to the secondary memory, retrieve it, and update the TLB again. So let's look at the structure of the TLB and how it works, like a visual representation of it. So as seen in this diagram over here, we have the CPU on the left, and we have the logical address here, that is the page number and the data contained. So once the page number, that is the logical address, is given by the CPU, it is passed to the, it is checked in the TLB if that particular page is present in the TLB or not. If it is present, then it is a TLB hit, and the it is immediately the mapped frame number is also given, and from the frame number we can easily access the physical address in the secondary memory or the main memory, and obtain the data. If in case the required page is not present in TLB, then it has to go to the page table or the page mapping table, and it has to look for it there. Even if again it's not present there also, then it's a TLB miss, and it has to go and check in the main memory. And once checking the main memory, if it was there in the main memory, then the TLB gets updated, and the value is added to the TLB, then the whole process is repeated. So if in case it is not present in the main memory also, then it has to go to the secondary memory and check whether the data is available in the secondary memory at least. So let's look at what is a TLB hit and what is a TLB miss in a more definition or a more formal way. So TLB hit is a condition where the desired entry is found in the translation Lookaside buffer. If this happens, then the CPU simply accesses the actual location in the main memory. So this is very efficient and very easy process, where it is a direct hit, and the corresponding frame number is also retrieved. So immediately we can access the location in the main memory. But in case if it is a TLB miss, so how do we define that? If the entry is not found in the TLB, it is a TLB miss. Then CPU has to access the page table in the main memory, and then access the actual frame in the main memory. So without just having the mapped data, it has to actually go and search for the data in the actual frame in the main memory, because we do not have the entry in the page table. So that is how we define a TLB miss. So these are the steps involved in a TLB hit. First, the CPU generates a virtual or logical address. It is checked in the TLB, if and it is present, because the TLB hit, it is present in the TLB. So the corresponding frame number is retrieved, which now tells where in the main memory the memory page lies. So immediately we get the frame number that is corresponding to that particular page, and we know where exactly which memory address in the main memory that particular frame is. So that is how those are the steps followed in a TLB hit. In a TLB miss, there are much more steps, because it's a much more complicated process. So first, the CPU generates the virtual or logical address, that is the page number. So this is the same as in the TLB hit. The starting is the same, and then it is checked in the TLB. So till this, it is the same as the process for the TLB hit also. But here, because it's a TLB miss, obviously the address, it's not present in the TLB. The one we are looking for is not present in the TLB. So now the page number is matched to the page table residing in main memory, assuming page table contains all the page table entries. So since it's not present here, we have to go and search in the page that is the page table that is corresponding to that particular page number. Each process will have its own page table. So corresponding to which page is requested by the CPU, that particular page table is taken from the main memory, and the corresponding frame number is retrieved from that page table. So here is where the process is complicated, because first it has to search and find the exact page table that page belongs to from the main memory, and from that page table then the exact page is retrieved. So this is where it starts to get becoming inefficient. So after that, the TLB is updated, because the TLB did not have this record, and it follows, as we saw earlier, it follows the most recently used algorithm, and now this page is the most recently used, so TLB is updated. So the new page that we had found in the page table is updated in the TLB. That particular mapping is updated in the TLB with the new page table entries, if there is space. If space is not there, then one of the replacement techniques come into the picture, like first in first out, or least recently used, or most frequently used. So as we are discussing here earlier, most recently used was also one of the replacement algorithms, but here there are some more. So first in first out is mostly like the FCFS, where it's almost like a queue. The first page that came in is the first to be removed in case there is no space. LRU is least recently used, which means the entry that was not used for a long time is the one that is removed first, and most frequently used is the one that is being used a lot now is retained or it is removed. So these are the algorithms that using which the entries in that TLB is managed if in case there is no space while updating a TLB. So once again we can take a look at the structure of the TLB. Take this time taking an example. So let's say the CPU asks for a page called page number 7. So here the here P, it becomes 7, right? So and then it looks in the TLB. Once it looks in the TLB, there is a table here. This table represents the TLB. So as it searches the first record, the second record, the third record, and when it by the time it comes to third record, here we can see the page number 7 is present in the TLB, which means this is a TLB hit. So it does not need to go and find that page table. No, that is already the TLB hit. So here the corresponding frame number is easily retrieved. So here we can see that the corresponding frame number is 11. So this number is passed on, and we can easily retrieve frame number 11 from the main memory. That is, we know that the physical address for that frame is 11. So here as you can see, it goes to the frame, and the frame number 11 is retrieved from the physical address in the main memory. So let's see another example where, let's say, there is a page number called 10. So the CPU generates a logical address with the page number 10. Here P becomes 10. So it starts to look in the TLB, that is the TLB cache. And once it looks there, it goes at the first record, it's 0, second record, it's 2, third record is 7. And that's all. The TLB is over, but there is no page number called 10. So it is a no. That is, it's a TLB miss. So it goes to the page table or page map of that particular page, and it checks there. So it is a TLB miss. So it actually searches in the main memory with that page table, finds that page and finds the corresponding frame number of that page and updates the TLB. So here 10 will be added. The page number 10 and its corresponding frame number will be added to the TLB, and again this whole process will be repeated. After updating the TLB, when the process is repeated, automatically 10 will already be in the TLB. So it will not become a TLB miss, it will become a TLB hit. So by updating the TLB, we can convert like a TLB hit into a, sorry, we can convert a TLB miss into a TLB hit. So that is how the translation Lookaside buffer works. So this was a very interesting concept for me to learn, as well as to be able to give this presentation. It was very it was a very interesting solution to a very complicated problem, and I thank you for your time, and thank you.